There we go. Good morning, everybody. This is a lesson for my grade 11 applied math students. We are going to be looking at a quick review of the graphing skills that you should have got from grades 7, 8, and 9. Why am I not mentioning grade 10? We'll do that one separately. So this one's just going to be grades 7, 8, and 9 graphing, all rolled into one quick lesson. All right, first of all, we're going to learn some language. You learned probably as early as grade 7 or 8 that all linear equations have graphs that are either constant or oblique. You learned that constant equations are equations like the line x equals 3 and y equals -2. And constant equations like those are either horizontal or vertical. Who remembers which one's which? Is x equals 3 the horizontal one, or is y equals -2 the horizontal one? So first of all, what do those words mean? If you need to add little things to these notes to make them make sense to you, please do. Horizontal, of course, means goes back and forth. Vertical means that it goes up and down. So which one's which? X is horizontal? That's incorrect.
What?
So let's go down to the bottom and let's graph those two. Here, I'll use a different color. I'll use blue. So I'm going to graph. What was the equation again? X equals 3. X equals 3 is this line right here. Now I know what you're thinking. I know why this is so poorly remembered by people, even though you did it last year.
No, we've done
Yes,
it
you
since
did.
grade 7.
Yeah, actually, yeah, that's true. You've been probably doing this since grade 7 or 8. The reason this is poorly remembered is because you've got it in your head that, wait a minute, this is my x-axis back and forth. But I want you to think about something. This is the equation x equals 3. What does that mean? That means x is always 3. What's this point here? 3, 0, 3, 1, 3, 2, 3, 3. All of these x coordinates along this line forever are 3. So logically, that's where x is 3. Y could be anything it wants. It doesn't affect the fact that x is 3. So now going back, let's use a different color. So this one here, oh, I've already highlighted. Let me get the highlighter off of there. There we go. So this one is the blue one, x equals 3. And let's use a different color. Let's use green. For green, y equals -2. That's a horizontal line, and it goes through -1, -2. So here's y equals, feel free to use a ruler if you have one. Unless you're so as good as me at, look at that, oh man. Unless you're as good at me as drawing freehand. Straight line, straight line, straight line, oh, okay. It's okay. So that's y is equal to -2. There we go. So yeah, so there we go.
I am going to defend the thinking of this class. To be fair, we thought of it as x-axis, not x itself.
Oh, but the equation, I asked you, what the equation x equals 3, is that horizontal or vertical? And everybody said, well, it's horizontal, but it's not. It's vertical. All right, so there's the first two. All right, what happens when you have more than one variable? You learned that equations in two variables, like x plus y equals 5 and 2x minus 3y equals 6, are called oblique lines. The word oblique basically means not horizontal or vertical. They're still straight lines. They're still linear. But what did they look like? Okay, so if we go all the way back to grade 7, the first way you learned how to put them on coordinate graphs was to make a table of values. So in either grade 7 or 8, depending on where you went to school, you learned to graph them by making a table of values. So let's do the x plus y equals 5 first. So let's just make 5x values. How about 1? Oh, hang on, I need a pen. Why aren't you working? 1, come on, pen. There we go. 1, 2, 3, 4, 5, and 6. So if x is 1, how much is y? So basically, what do you add to y to make 5? This is the way you teach it to grade 7s. So that's a 4, and then that's a 3, that's a 2, that's a 1, and then you freak out your grade 7s by having integers after the 0, so -1. And of course, you can graph it that way. Let's pick a color for this one. Let's graph this one in purple. So let's just graph it. So let's take a look. We have all these points. 1, 4 makes a point. So 1 over 4 up is right there. 2 over 3 up. 1, 2, 3. 3 over 2 up right there. And you'll notice at this point why it has the name linear. If you graph all these points forever, you get, of course, a straight line. 6 over 1 down. And again, I'm going to try to just sort of freehand this. Maybe if I just kind of follow along that grid. That's pretty good. I'm pretty happy with that one. So that's x plus y is equal to 5. Label it. If you don't have different colors, just make sure you label really good. Now, remember that I made a table of values, but obviously that's not all of the values. It's just some of them. What about all the values between the integers? They count too, right? I have 1, 4. I could have 1.5, 3.5. I could have 1.007 and 3.993, right? There are infinite pairs of points along this line. In fact, you could even say that this line and all of the infinite pairs of numbers are the solution to this equation, right? You probably first saw equations as things you have to solve. If I have only, you don't have to write this down. If you only have one variable, you have all kinds of algebra tricks you can use to solve for that variable, right? You'd add 1 to the other side. You'd divide both sides of the equation by 2. Now that bracket doesn't mean anything. I didn't divide by 2. Now that bracket doesn't mean anything. Then I'd minus 3. Hey, look at that. X was 0. Okay? That was, right, that's basic grade 8, 9 algebra to solve equations, right? Like, whatever grade you saw it in for the first time. Doesn't matter. So anyway, this is solving an equation. So that one's fairly complicated. It had brackets. In grade 9, you even had ones where you had x on both sides. But this is a very easy-looking equation. But if I said to you, solve it, what do? Well, there's infinite solutions, right? It could be 1 and 4, or 4 and 1, or 0 and 5, or 5 and 0. All of the infinite solutions that make this a true equation are on this line. That's why we wanted to graph it in the first place. Graphing allows you to find solutions that you wouldn't be able to find by algebra, because your algebra is limited to being able to solve for one variable at a time. The only way I could solve for 2 variables is if I had 2 equations with the same 2 variables. And we'll get to that later this chapter. Okay, so anyway, that equation had that for a table of values, and we graphed it. Let's make a table of values for the other one. Now, this one's kind of not as much fun, maybe. Let's do this one. I need a new color. Let's do this one in red. This one here, if I pick the same x numbers, 1, 2, 3, 4, 5, and 6, ooh, this is a bit of a drag. There's actually only one here that's easy. If x was, well, there's 2 here that are easy. If x was 3, let's do the 3 one first. If x is 3, you plug a 3 in for x, and you're going to have to do a little bit of algebra. You're going to have 2 times 3 minus 3y is equal to 6. And this is why this is maybe the kind of question you do in grade 8, not grade 7. So you'd go 6 minus 3y equals 6. You'd subtract 6 from both sides. And now you divide both sides by negative 3. And aha, this is 0. An integer. What's the only other one on here that's going to end up being an integer? See if you can figure it out before we play. No, 3 makes 0. Right? Because what was my last step of algebra? I divided both sides of the equation by negative 3. And 0 divided by negative 3 is still 0. Of all of these other potential x's, what's the only other one that'll give me an integer? Nope, 1 won't. Let's try 1. 2 times 1 minus 3y equals 6. 2 times 1 is 2, minus the 2 on the other side, and negative 3y is equal to 4. Nope. Y is going to equal negative 4/3, I'm sorry to say. Is it 2? Nope. 2 is going to give me negative 2/3. It's 6. Why is it 6? Because 6 has a factor of 3 in it. Ha-ha. So let's try first of all, can you see the actual pattern here? Maybe we don't have to do any more algebra if we can see the pattern.
You actually don't.
What pattern are we doing? We go negative 4/3, negative 2/3, 0. What are we adding every time?
Plus 1.
Nope.
1/3.
1/3.
Nope, not quite 1/3. We're adding 2/3 every time. So add 2/3 and I get 2/3 to 0. Add 2/3 to 2/3 and I get 4/3. And then you're probably thinking, wait, you said this one's going to be an integer. Yeah, what's 6/3 simplify to? Yeah, 2. And there's the ideas that you learned about in grade 7 and 8. That there's patterns to this. Like even this one had a pattern, right? This pattern was very easy. I was just going down by 1. This pattern's a little more complicated. I'm going up by 2/3. Then in grade 9, you started to formalize that idea that you're going up by the same amount. You go up by 1 every time you go across by 1. And this one, you go up by 2/3 every time you go across by 1. Because remember, x is going across and y is going up and down. What did you call that relationship of rise over run? It has a name, begins with an S. Slope. In grade 9, you started calling it slope, even though by grade 8, you'd probably figure it out already that this is the way the patterns worked. In grade 9, you called it slope. The other thing you learned about in grade 9, besides slope, was that assuming the line's oblique, it's not horizontal or vertical, it has to hit both the x and y axis somewhere. And we call those the x and y intercepts. And for an equation like this one, those are easier to find usually than a table of values is. So your grade 8 teacher taught you, hey, we don't need tables of values. We're not babies like grade 7ers anymore. We can just find the intercepts. You can say the x-intercept happens when y is 0. So plug in a 0 for y. And then what's 3 times 0? 0. So this algebra simplifies super nice. It's just 2x equals 6 and x equals 3. We kind of knew that point already. It's right there. But you get the idea. Let's find the y-intercept now. The y-intercept happens when x is 0. Does that logic make sense to you? Let me just go look at the graph for a sec. Don't worry, I'll come right back. Remember, on a grid, every single x coordinate along the y-axis is 0. Right? This is 0, 0. This is 0, 1, 0, 2, 0, 3, 0, 4. And then when you're on the x-axis, every single y coordinate is 0. Right? This is 0, 0. This is 1, 0, 2, 0, 3, 0, 4, 0. So that's how you solve for the intercepts. You say, okay, I want the y-intercept. Where does it cross the y-axis? Oh, it crosses it when x is 0. So in my equation, 2x minus 3y, I get 2 times 0 minus 3y equals 6. So 2 times 0 is nothing. So y is equal to negative 2. So why is that an easier way to graph? Because now I know 2 points. That's all you actually need to graph a straight line, is all you really need is 2 points. Your grade 7 teacher was wasting your time a little bit by making you make these great big charts. They wanted you to see the pattern too. That was the important part. In grade 7, it's all about pattern. But by grade 8, we just need the line so we can think about it and look at it. And you only need 2 points to graph a straight line. So if I know that this line here hits the x, and let me say that again. If this line here hits the x-intercept at 3, 1, 2, 3, and it hits the y-intercept at negative 2, there is my graph. So there it is. So there's the other graph we have to draw. And we'd say that to draw this graph, you have to go up 2 points and over 3 points to get from one point to the next. So I need another point. Let's keep drawing. Go up 2 points and over 1, 2, 3 points. Up 2 points and over 3 points. And again, this up and over, you learned in grade 9, is this number here. Rise over run, aka slope. So for my second equation, what was it again? 2x minus 3y equals 6? For my second equation here, to get from one point to the next, I always have to go up 2 and over 3. What if I wanted to go backwards? No problem. Go down 2 and left 3. Down 2 and left 3. That's a heck of a lot easier than trying to graph the points that I got in my table of values that have fractions on them. Blech. And that's where you got to in grade 9. In grade 9, you would have found a way to graph this line. You'd have actually graphed the other one this way too, by changing these two equations into a form that has the slope right in it. And you remember that now probably as y equals mx plus b. Do you remember that? So the first equation here is x plus y equals 5. Let's rearrange it so that it looks like y equals mx plus b. Well, that's pretty easy. All I have to do is subtract x from both sides of the equation. And there it is. So this equation here has, and remember I was doing this in purple. Let me do this in purple. Oops. So this is y equals negative x plus 5. What does the m number? What is the m number in this equation? What's the number in front of x? Negative 1. So the m number for this is negative 1. Now I have to think about that as a fraction. All numbers have a denominator. If they don't write it down, what do you assume it is? 1, correct. So I have a rise of negative 1 and a run of 1. I can see that in my graph. Remember, we already graphed this one from our grade 7 table of values. Pick any point on this graph. There we go. That one's a good one, the y-intercept. And then go down 1 over 1. Down 1 over 1. Rise of negative 1, run of positive 1. Is that looking familiar? That's the way they taught you how to graph in grade 9. They said you can leave those tables of values behind. And you can use intercepts if you want, but even that isn't as easy as just saying, I have a b value of 5. Who remembers what the b value means? It's the y-intercept. I hit the y line at 5, and then I go down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. Let's do the other one now. The other one I did in black. The other equation was, I'm kind of running out of room here. The other equation was 2x minus 3y equals 6. Write small. Okay, rearrange that so it looks like y equals mx plus b. And this is where somebody looked at the first page of the booklet yesterday and said, oh no, fractions. Don't even think of them as fractions. Think of them as slopes. Step 1, minus 2x from both sides. Now it's a negative on the other side. Step 2, I need y by itself. What's this negative 3 doing to the y? It's multiplying. How do I undo that? Divide both sides of this equation by negative 3. So this number becomes negative 2 over negative 3. Are you okay if I just cancel those negatives? A negative divided by a negative is a positive. And then positive 6 divided by negative 3 is negative 2. So my slope number is up 2 over 3. My y-intercept number is negative 2. So if I want to graph this line, here, let's just start over. Y equals 2/3 x minus 2. What does that tell us? It tells us it hits the y line at negative 2, and then you go up 2 and over 3, and that's how you graph straight lines in grade 9. Up 2 and over 3. Up 2 and over 3. Notice how we're getting the exact same line we had before? Oh, I want to go backwards. So what do I do to go backwards? Go down 2 and left 3. Just do the opposite. Down 2 and left 3. And that's grade 9 graphing. Slope and y-intercept. Y equals mx plus b. And that's how you learned how to graph lines in grade 7, 8, and 9. You started by just, well, you don't really know much about them. You might see the pattern in them. So take the numbers from the pattern list from the table, plot them, and join them with a ruler. Yay! In grade 8, we wanted you to be a little more sophisticated. So we go, okay, let's play with our new algebra skills. Figure out how much y is when x is 0. Figure out how much x is when y is 0. And then you graph them maybe by intercepts. But by grade 9, you should be comfortable with your algebra enough to rearrange things. And we need you to be able to do that again. Okay, on the next page, it looks like we're changing gears almost completely. Because something else you learned how to do in grade 9 was draw pictures of inequalities on a number line. Remember this? How do you draw me a picture of x is greater than 3? Well, x, think about first of all, what does this mean? Well, x could be 4, it could be 7, it could be a billion, it could be 3.0001. All of those things are bigger than 3. Is 3 bigger than 3? No.
No.
So to show you that I'm not including the number 3, do you remember how you did this? You drew an open circle, do you remember that? And then an arrow going that way. Is that starting to come back to you a little now? Okay, let's draw the next one. What does this sign say? Less than and equal to, or you could use the word and or here interchangeably. Less than or equal to -1. So -1 counts, but so does -2, -3, -4, and -1 billion. -1.75 is in there. -pi. All of those numbers make that a true statement if you plug them in for x. How do you draw that?
Put a circle on top of.
Fill in your circle because this number counts this time, but now the arrow is going that way. Now, what do you do with the third one? What's the third one saying? Math. I'm sure you've heard the analogy that math is like its own language. Some languages, when you read from left to right. Pretty much all Western languages. Some languages read right to left. A lot of your Middle Eastern languages. Japanese, you read top to bottom.
You read from right.
Good old math, you can start reading in the middle and then go both ways. X is greater than or equal to. There might be people going, wait a minute, that's a less than sign. Not when I read going to the left. X is greater than or equal to -2, but it's less than or equal to 1. So what am I telling you? It's between numbers, but wait a minute. It's between these two numbers, but it can't be 1 because it doesn't. Oh, wait a minute, it can be 1. Oh, sorry, they're both solid. I'm sorry, I thought I had written this so that one of them didn't have an equals, but they both have an equals. So it's a solid dot here, and oh wait, no, it's not. Sorry, it's a solid dot here. Thank you, and it's a solid dot here, and then you just draw a line. Okay, I'm going to add one. You try one. What if I had one? You can just draw it on the same. Draw it above it or something. What if you had x was between, say, -1 and 3, but notice carefully, I didn't put an equals on the 3 one. So what does that mean? What numbers make this a true statement? Well, 0 does. -0.5 does. 2 does. 2.5, 2.6, 2.7, 2.8, 2.9 does. 2.99 does. 2.99999 does. But 3 would make it false. 3 is not less than 3. How do I draw that? I put a solid dot here, because I can be -1.
And all the way to 3.
And all the way to 3, but what kind of dot do we want? Open. So there, that was our kind of quick and messy review of grades 7, 8, and 9 graphing skills. So I'm going to stop this video so people who have these skills already don't have to watch this one if they don't want to. And then we're going to start our new booklet.
So you only shade.
Thanks for watching.